tightly on the board. So what we have learned from Professor Blanda's lecture is that we have a basis which is, okay, we are independent of the, since we do it independent on the choice of the basis, of course, but when we start, it's easy to see nothing well to space. So it's very close to the basis in Dracula algebra, in the exterior algebra, except that we have identity. So we have, let's say, three independent unit vectors in space. I'm going to separate, this is the grade 0 part, this is the grade 1 part, one vector. And then we have two vectors. Okay, I'm going to write E1, 2, E, or maybe I'm going to do the way we usually do in physics. 1, 2, 3, then this is 1, 3, and this is so this is the grade 2 shadow slide vector. Because we can write Eij instead of Ei times Ej. Just a short notation. If the Clifford product are the two vectors, but since they are independent as vectors, that's how we choose the basis, because it's the most convenient, most obvious way. So therefore the Clifford product, of course, is the exterior product. So this thing is already associated with the plane spanned by the two vectors. If we go further, we have in 3 dimensions nothing more than a 3 vector. We cannot go further because obviously the flow volume of 3 dimensions is 0. This is a volume element, or as we call it, this is the highest grade, as we call it the pseudo-scalar. So apart from the scalar, we have a pseudo-scalar. So the other thing which is 1 dimensional, the other thing which is 1 dimensional, is spanned by the volume element. Okay? This is E1, E2, E3. The determinant is like the matrix algebra, is the determinant of the mixed product of the triple product. Okay? So let's see how these things work. If we want to consider the triple algebra wasn't to do more this way. Let's go to see how this works. Let's construct this from scratch. So we have 3 unit vectors. Right? And we have this condition that it was like the corridors. Yeah, actually, this already tells you everything. So you have to know more basis. And then what are these going to be? Well, as Professor Gonzalez explained, these are the quaternions. So if we take only the even grade algebra, it's usually denoted by this. These are the quaternions, which are, maybe I should have written first in Clifford notation. 0, 2, which is one of the very few Hurwitz algebra, one of the very few non-division algebras. We only have a couple of those. You have the units, you have the complex, you have the quaternions, and of course you have the quaternions, which are not associative. So this is although it has to do something with different algebra and classical groups, this is not a different algebra, but those ones are. And you have you're not, okay, if you want to preserve invertibility, the division property, you're fixed to this path, okay? This is the system of the development process, but you can make different generalizations. Okay, for example, instead of the complex numbers, the so-called hyperbolic or split complex numbers also do not apply. Here you also have, for example, the big complex numbers, or you have the split quaternions. Okay? Here you also have other options. For example, you have the biquaternions, complexification. These are all Clifford algebra, so everything without this one is a Clifford algebra. So it's good to follow a path starting from the simplest thing. So it's very easy if you have the complex numbers to isolate the real components and say, okay, this is some sort of continuation, prolongation of the complex numbers. So if you know quaternions, it's very simple. If you know quaternions, we can go a little further. I'm going to use I, J, and K for this one. All three of them square to -1. And of course, they have this beautiful multiplication table. I, J, equal K. Wait, the way I've written those, is going to be, there's going to be one minus. There's going to be one minus. Because they use the notation, the convention is that we order the indices.
The expression I have written before about expressions, written with I joint K must change.
Yeah.
Quaternion and the inverse quaternion for the because of there is a change of sign between
This is the same object, but it depends on the perspective from which you look at it. If you look from the three-dimensional perspective, you have to be careful. If you want to look from the two-dimensional perspective, so forget that there is a three-dimensional space. You can think that we only have two-dimensional space, but the squares of vectors are negative. Okay? So this is the Clifford algebra. This notation again. This notation means that there's a metric which defines the Clifford algebra, but in the form with 0 pluses and 2 minuses. Okay? So the orthonormal basis would be with -1. And if you start from here, you have two vectors, I which squares to -1, of course, j which squares to -1, and this is a pseudo-scalar. This is the volume form, is a two vector because you have two-dimensional space. And it's not difficult to see that it also squares to -1. We call this k, okay? Because it's just the next best example. But anyway, one should be careful with the definition, but still, this is the same algebra. It is a sub-algebra because what Professor Vargas said is a particular property of Clifford algebra. You have a Z2 grade, so you have the even and odd grades. You don't have degrading which you know polynomials have. Right? So something is either even or odd. But if you multiply two odd things, you get an even thing. So this is not a set of algebra. But for even rates, it's the cost of the multiplication. So you have your quaternions embedded. Okay? So if you want to start with quaternions, the way you construct complex numbers from reals and quaternions from complex numbers, right? So quaternion can be written as G1 plus, well, let's say plus double J. With Z and double are complex numbers. So pretty much it's very similar to the construction of complex from reals. Okay. So if you want to go from here, from non-quaternions, you construct the whole space algebra, just three-dimensional space algebra. What do you have to do? It's something similar. You have two quaternions, let's say Z and W, okay? Now they're going to be quaternions. And you want your elements. How should I call this thing? Maybe big letter I. You want this to be a representative of the space algebra. Okay. What would this thing be? It's an analog of the imaginary unit, right? It's an analog of the imaginary unit. You extend your even subalgebra into the whole Clifford algebra. But it turns out it is the very imaginary unit because this is actually the so-called pseudo-scalar. It has this very nice property that it squares to -1. And you commute all elements of the algebra. So it has the very algebraic property of the definition of the imaginary unit. So you can actually, okay, it's not nice because I used IJK following Hamilton, but okay, this I would be different I. But this I is the imaginary unit. So it turns out just as an algebra, this is just a complexification of the quaternions. Okay. And if you want to follow this process from two-dimensional to three-dimensional algebra, two-dimensional space to three-dimensional space, the next one will be the one of space-time. So if you want to continue with this, so you have the quaternions, which I'm going to write in different algebra, which are the even dimensional subalgebra of the three-dimensional one. Okay. So the next one would be space-time. Okay. 3, 1 or 1, 3. They are different algebra, but this embedding is true in both cases. In terms of the even subalgebra, there is no difference. So, but this is for the next lecture. This is how